Welcome again, my friends and followers. Let us talk about condensation, heat transfer coefficient. How can we estimate the condensation heat transfer coefficient of fluids as they pass through the tubes? It is meant here to talk and present the condensation process when we have internal flow in the tubes. Let us go to some details of this subject. Welcome, my friends and colleagues and followers. The condensation process is one of the important topics present in modern industrial applications in the field of energy and heat transfer. We may find the condensation process in many topics and fields of industry, such as petrochemical factories, refineries, food industry, power plants, air conditioning and refrigeration, and many other topics that is experienced in the field of thermal engineering. The prediction of condensation process and the performance of a heat exchanger is mainly based on the heat transfer coefficient and how accurate it has been predicted. Condensation can occur in different orientations: vertical, horizontal, single, or tube bundle. And in the present episode and the film episodes and videos, I will introduce the condensation process in different categories, whether it was external or internal flow. Thank you for your support and continuous assistance that is afforded by your side to the channel, and let us go directly to the objectives of the present episode. The main objectives of the present video are related to concept of internal flow condensation in vertical tubes. And then we will pass through some of the available correlations to predict the condensation heat transfer coefficient in vertical tubes. And finally, we will arrive to the closure of the present episode. The concept of condensation process in vertical tubes can be described by using this illustration. Let us consider an industrial site where a condensation process occurs in a vertical orientation heat exchanger as shown here. Let us consider that the flow passes through the tubes, and on the external side, we have cooling water on the shell side as shown in this figure. And the condensation process occurs as the vapor enters from the top of this tube. We may make this process um, clear by referring to this figure. Let us consider the vapor flow from the top of this vertical tube enters at the top side, and if it was superheated vapor, then we should desuperheat this vapor before getting condensation, and that means we have to reach the saturation temperature of that vapor, and we have X equal to 1. As the cooling process continues, then a part of this vapor is condensed, composing a thin film adjacent to the internal surface of the tube. And this process continues until we get a part of it to um, disperse in a drop form as shown. Then we will get a sort of misty flow, and finally, when all the vapor is condensed, where we reach X equal to 0, then the condensation process has finished. This part is called condensation zone, and sometimes this liquid is cooled down to a temperature lower than its saturation temperature. It is called subcooled um, process, and usually this process, the subcooled liquid process, um, is experienced in most of the industrial sites in order to improve the thermal efficiency of the plant. Of course, on the left-hand side of this figure, we may see the description of these forms of condensation, that is single phase, then we have annular mist flow, then laminar, then we will reach a transition region to a turbulent flow, and finally we have the subcooled region where we usually experience a single phase liquid. This is briefly how the process of condensation uh, takes place inside a vertical tube. Available correlations for condensation process in vertical tubes. Of course, there are quite a good number of these correlations are available in the open literature. Let us introduce first Nusselt equation in 1916 when it was performed through analytical solution for condensation process on a vertical plate. And this correlation has the form as shown in equation 1a. And this equation, of course, has the same form or similar to those used in the condensation on outside of tubes. And this correlation depends on the condensate tube loading as defined in equation 1b, and it is applied for a vertical tube orientation. We have also Boyko and Crozilin 1967, they suggested a correlation in the form of equation 2a, and we have hi, the mean value, as shown in equation 2b, where a coefficient of 0.021 is used with Reynolds to power zero point 0.8 and Prandtl to 0.43. And a complete condensation of saturated vapor to saturated liquid in vertical tube for description of this equation, which can be used in such condition. We have also Shah correlation in 1979. He presented a correlation depending on the heat transfer coefficient of two-phase flow, as shown in equation 3a. And we have H sub LT refers to the heat transfer coefficient when all mass flowing inside the tube is assumed as a liquid, which can be calculated from this form in 3b, where G represents the mass velocity or mass flux of the flow rate of vapor inside the tube. We have the definition of Nusselt number, which is 0.023 Reynolds to power 0.8, Prandtl to 0.4, as shown in equation 3c. And this correlation assumes annular flow in the horizontal and vertical tubes, and it is valid for restricted correlation conditions as shown in this forms for Reynolds number for the gas and Reynolds number for the vapor, the inside diameter of the tube, and the heat flux U double dot in units watt per meter square. And this correlation predicted the experimental data within a mean deviation of 15.4%. Shah in 2009 has presented in fact, three correlations depending on the zone of flow. That is the first, second, and third zones, and these zones depend on some conditions which are depending on Reynolds number, of course, and he presented the correlation in a form similar to the old one which has been mentioned in Shah as a reference number 3, and we have H Nusselt and H sub LT, and these values are used depending on the zone where we are dealing with, and Reynolds number in equation 5a represents that the Reynolds number for the liquid phase where it flows alone in the tube, and it is expressed by G times 1 minus X, because X we have the quality of vapor, and he stated that this correlation can be applied to all types of flow orientations, and the use of Hi sub I, which refers to the first zone in equation 4a, and equation H Nusselt in 5a, or H of two phase as represented in equation 3a, or any combinations of these two has been described by Shah in reference number 4, and how can we recognize these regions and how can we use these relations. And you may go back to this reference to have a look on the way how this correlation can be applied, or you may go back to my book, which I have already published, entitled The Principles and the Practice of Heat Transfer. And we have many correlations there and many practical examples on how to use these correlations. Now we have arrived to the final section of this episode. We passed through the concept of condensation in vertical tubes, and we described the regions of the flow, desuperheating, condensation zone, and finally we may have a subcooling zone. All the regions and how the type of flow is single phase, mist flow, annular, and finally, we will reach for the subcooled region where we have a single phase liquid. And at the entrance of the tube from the above side, we have also single phase vapor. And we may use convection heat transfer coefficient correlations for that. And these correlations have been described in our previous episodes when we talked about convection heat transfer. And then we mentioned some of the available correlations and how to predict the heat transfer coefficient for condensation. Don't forget that we have a list of some valuable resources for condensation seated in the description box. You may consult them. And thank you for listening. And if you found the content of the present video are useful to you and others, please subscribe and share it. And don't forget to hit the like button below this video. I will see you in the next part of the same subject for condensation about in vertical tubes and with a practical case study. Bye bye.